Good morning, students. I'm Dr. Betty, continuing with the nuclear chemistry, lesson 5. In lesson 4, we looked at the nuclear reaction, and we said a nuclear reaction is a reaction in which one element is converted into another element. This can take place either by spontaneous disintegration or by bombarding an element with a suitable bombarding particle, which was referred to as an artificial transmutation. We said in the nuclear reaction, alpha or beta particles are emitted. And we also went further to say that in a nuclear reaction, new atoms are formed. We looked at the differences between a nuclear reaction and chemical reaction. We said in a chemical reaction, outermost electrons participate in the formation in the reaction, while in a nuclear reaction, the nuclei of an atom undergo a change. We also said that in a chemical reaction, a small amount of energy or heat is absorbed or released, while in a nuclear reaction, a larger amount of heat is absorbed or released, and many other differences. We looked also at the classification of nuclear reaction, where we said that the first classification was based on whether the nuclear reaction takes place spontaneously or is brought about by an artificial means, and so many other classifications. Today, we are going to look at nuclear fission. You can ask yourself, what is a nuclear fission? This is a nuclear reaction in which unstable heavier nucleus, an example is uranium, on being bombarded by slow-moving neutrons, split up into two lighter stable nuclei of almost equal size, and at the same time emitting neutrons and releasing very huge or very large amount of heat energy. You can call it nuclear energy. So uranium-235 being bombarded by slow-moving neutron, it gives rise to the formation of stable 141 boron, barium, plus 92 krypton, and 3 neutrons, and huge amount of energy are released. Now, amount of energy liberated in the fusion of one atom of uranium-235 can be obtained as in the fusion of 235 uranium nucleus is an exogic reaction, that is, heat is released. So the energy released is called the nuclear energy, or the atomic energy, or fusion energy. So as we said earlier in the first slide, that uranium-235, when bombarded by the slow-moving neutron, it gives rise to the formation of a stable 139 barium plus 92 krypton and 3 neutrons, plus a large amount of energy is given out. So this energy is the one which is called nuclear energy or atomic energy. The energy released is calculated with the help of Einstein's mass energy, which is equal to mc squared, where E is the energy released, m is the mass lost, c is the velocity of light. So if the mass lost is given in mu, then the energy released is equal to, or energy energy released is equal to the mass lost times 931.5 milli-electron volts. And you remember the mass lost can be obtained as sum of the masses of the reactant minus sum of the masses of the product times 931.5 milli-electron volts. So masses of the reactants are equal to the mass of uranium-235 plus the mass of the slow-moving neutron, which is equal to 236.052 mu. Then mass of the products is equal to the masses of the barium-141 plus mass of the krypton-92 plus the 3 neutrons, which is equal to 235.837. Therefore, mass lost is equal to the difference between the products and the reactants, which is equal to 0.215. Therefore, the energy released is equal to 0.215 times 931.5 milli-electron volts, which is equal to 200.27 milli-electron volts. So this is the energy that is obtained by the fusion of one atom of uranium. Amount of energy released by the fission of 1 gram of uranium. The number of atoms present in 1 gram of uranium-235, let us take the Avogadro's constant to be equal to 6.022 times 10 to the power 23 atoms. Therefore, 235.0 grams of uranium contains 6.022 times 10 to the power 23 atoms. Therefore, 1 gram of uranium will contain 6.022 times 10 to the power 23 divided by 235. And the answer we get here will be the number of atoms that are containing in 1 gram of uranium. We have already seen that in the previous slide that the energy released by the fission of 1 gram of uranium is equal to 200.27 milli-electron volts. So the energy released by the fusion of 1 gram of uranium will be equal to 6.022 times 10 to the power 23 over 235 times 200.25 milli-electron volts. So converting this energy into kilojoules, we shall convert the milli-electron volts first. So 1 milli-electron volts is equal to 10 to the power 6 electron volts. And 1 electron volt is equal to 1.602 times 10 to the power negative 17. So multiplying by those factors to convert the milli-electron volts to joule, this will be equal to 6.022 times 10 to the power 23 times 200.27 times 10 to the power 6. Now there I'm converting the electron volts times 1.602 times 10 to the power 19, now into joules, over 235. And if we want to change it to the joules into kilojoules, so we shall divide the resultant answer by 10 to the power 3, which is equal to 6.22 times 10 to the power 7 kilojoules. Uses of atomic energy or nuclear energy. It is used for generating electricity Atomic energy is used for the treatment of diseases like cancer, used for the improvement of agriculture and industry. Now, an assignment I can leave you with is write brief notes on the explanation of the nuclear fission of uranium-235 nucleus by liquid drop model. Types of fission reactions. There are mainly two. We have the uncontrolled or explosive fission reaction. You remember in the reaction of uranium being bombarded by slow-moving neutrons, it produces 3 more neutrons. If none of these 3 neutrons produced in the fusion escapes out of the air, then each of these 3 neutrons causes the fission of another uranium nucleus and produces heat energy. The 3 neutrons causes fusion of the 3 more uranium nuclei and produces 9 neutrons along with a lot of more energy. Again, these 9 neutrons causes the fusion of more 9 uraniums, producing 27 neutrons, and greater amount of energy is also produced. So this process of fission of uranium goes on like an ending chain of fission reaction, and eventually an uncontrollable amount of energy is produced in the short time. This energy cannot be used for production of electricity. Rather, it causes an explosion in a few minutes. Since these reactions take place at a very fast rate, it cannot be controlled and produces a tremendous amount of heat energy, which causes explosion. So this reaction takes place in an atomic bomb. An illustration is given as we said a slow-moving neutron bombards uranium to give the barium and krypton and 3 neutrons. So if these neutrons are not controlled, they also bombard other uranium, giving rise to the formation of 3 neutrons each. And then also these ones bombard more uranium, giving rise to a lot of heat. Control or critical fusion reaction. That is the second type of fusion, controlled or critical fusion reaction. If two of the 3 secondary neutrons are absorbed by cadmium or boron rod before they can cause the fusion of another uranium nuclei, only 1 neutron is left, which causes the fusion of one other uranium-235 nucleus. This fusion reaction proceeds at a steady and slow rate, and hence controlled amount of energy is produced. Since this fusion reaction takes place at a steady and slow rate, the energy can be converted into electricity with the help of an atomic power plant. The reaction is also called the critical fusion reaction, since this reaction takes place when uranium-235 has a critical mass. Let us look at a nuclear reactor or atomic reactor. A nuclear reactor is a kind of furnace in which controlled fusion of radioactive material like uranium-235 take place, and a manageable amount of nuclear energy is produced at the steady and slow rate. Nuclear energy produced is in the form of heat energy, and this heat can be converted into electricity in a nuclear power plant. Components of a nuclear reactor and their functions. The first component is a moderator or moderators. The fusion of uranium-235 nucleus by slow neutrons, we said it produces 3 neutrons, which have very high speed. So since the secondary neutrons are fast neutrons, they cannot cause fusion of another uranium effectively. So in order to enable these neutrons to cause the fusion of uranium-235 nuclei more effectively, the speed of these neutrons must be slowed down. The speed of the neutron is slowed down by using the substance like pure carbon, call it graphite, heavy water, and others inside the reactor. And these substances are called moderators. The moderator, therefore, is a substance which slows down the speed of secondary neutrons produced in the reactor to a level at which neutrons can cause the fusion of other uranium nuclei. Another part is a controlling rod. So in order to regulate the excess number of neutrons, cadmium or boron rods are used. The controlling rods regulates the number of neutrons that can cause the further nuclear fusion of uranium-235 nucleus, and thus controls the rate of fusion and controls the amount of energy obtained per unit time. This controlled amount of heat energy can be converted into electricity. Then the third part is the fuel element. Uranium-235 isotope undergoes nuclear fission and hence acts as the real fuel element. Enriched aluminium is used in the form of long rods or plates. These uranium rods are inserted into the graphite core in such a way that cadmium or boron rod lie in between the uranium rod. Another one is a coolant or heat transfer agent. Remember we said that the bombardment of uranium with the slow-moving electron produces a lot of energy. So the energy produced in the reactor is in the form of heat. It must be quickly transferred to heat exchanger. The transfer of heat energy to the heat exchanger is done by cycling a coolant in a pipe, which is connected to both the reactor and the heat exchanger and forms a coil inside the heat exchanger. The coolant is pumped into the reactor. In most reactors, liquid sodium metal is used as the coolant, which transfers the heat energy to the heat exchanger in a short time. In some reactors, carbon dioxide gas, water are used as coolants. Heavy water, organic compound are also used as coolants. A point to note here is that the coolant must have high boiling point and high specific heat. Now we have been talking about coolants. You can ask yourself, what are a coolant? So what is a coolant? This is a substance which transfers the heat energy produced in a reactor to the heat exchanger. Then we have the shield. shield or protective screen or protective chamber. All the above components, that is the moderator, controlling rod, and fuel element, are enclosed in a chamber which has thick walls made up of cement and concrete. These walls stop the nuclear radiations to go out of the reactor and save the human beings and animals from their dangerous effects on them. We say that the concrete chamber acts as a shield or a protective screen and is called a protective chamber. Uses of a nuclear reactor. Radioactive isotopes of various elements are produced, and these isotopes have been found to be very useful in pure science, biology, and medicine. Heat energy produced in the fission of uranium-235 nucleus by slow neutrons in the atomic reactor has been used to generate electricity. It produces fissionable material like plutonium, which is used in atom bomb. It is also used for the production of fast neutrons that are needed for the nuclear bombardment. Let us look at an atomic bomb or fission bomb. An atomic bomb consists of several thousands of pieces of uranium-235 isotopes. The masses of each of the pieces should be less than the critical mass of uranium-235 isotope. But the sum of all the masses of all the pieces should be greater than the critical mass of uranium-235 isotopes. Between each of the pieces, explosive material like trinitrotoluene, TNT, is also placed. When TNT is fired, the different pieces of uranium-235 rapidly come together and form a larger piece of uranium-235 greater than the critical mass of uranium-235 isotope. Now neutrons obtained from radon beryllium source are allowed to strike the larger piece of uranium-235. This results in the rapid uncontrolled chain reaction. This reaction takes place at uncontrollable speed, leading to an explosion and hence to the production of unmanageable quantity of heat energy. So we have been talking about the critical mass. So what is a critical mass? This is the minimum amount of fissile material required in a nuclear reactor or a nuclear weapon to sustain a chain reaction. So the amount of energy liberated in an atom bomb is equal to that produced by about 20,000 tons of TNT. This energy raises the temperature to the order of 10 million degrees Celsius and more, and produces a pressure of several millions atmosphere. The explosion also produces a violent and intense blast of visible ultraviolet, X-ray, and gamma ray radiations, which cause blinding flash. When fission occurs, The fragments fly apart with great speed. They collide with each other, and then kinetic energy is changed into heat energy. The radioactive fragments formed scatter over wide area and get deposited onto the surrounding objects. These deposited radioactive fragments and different type of radiations have very bad effect on living and non-living objects. So next time we are going to look at nuclear fusion.